Today, we're diving deep into the anatomy of a nationwide power failure. It's a fascinating story, really. It's about how a single bolt of lightning and, get this, a single line of code managed to plunge 1 million homes into darkness and bring the country's railways to a grinding halt. So that's the central mystery we're unpacking today. How on earth does one pretty common lightning strike set off a chain reaction so specific that it strands over 1 million people? It seems impossible, right? Well, let's find out. So let's set the scene. It's a completely normal Friday afternoon, August 9th, 2019. The UK's electricity grid is just humming along. It's doing what it does every second of every day, perfectly balancing the supply of electricity with our demand for it. Everything is stable. Then, at just 2 minutes to 5 in the evening, a summer storm starts brewing. Now, for the national grid operators, this is totally business as usual. I mean, they deal with over 1,000 lightning strikes to their network every single year. So the storm was expected. What happened next, though? Absolutely was not.
Okay, before we go any further, there's one really crucial concept we have to get our heads around. It's called system frequency, but you can just think of it as the grid's heartbeat. In the UK, that heart has to beat at a rock-steady 50 hertz. Now, that stability traditionally comes from the sheer physical momentum of massive spinning turbines in power stations. It's a concept engineers call inertia, and it acts like a giant shock absorber. If that heartbeat goes too fast or too slow, the whole system is in critical danger.
Right, so let's get to the incident itself. This wasn't just one thing going wrong. Oh no, this was a breathtakingly fast chain reaction. The dominoes were all lined up, and they were about to fall fast.
Just look at this timeline. It's incredible. At 16:52 and 33 seconds, bang, lightning hits a line. A totally routine event. But then, just 1 second later, a steam turbine at Little Barford Power Station trips and goes offline. 1 second after that, the huge Hornsey offshore wind farm trips. And then, less than a minute later, another turbine at Little Barford just gives up. 3 massive sources of power just gone, in the blink of an eye.
So you're probably thinking, doesn't the grid have a plan for this? And yes, it does. It holds a certain amount of backup power called reserve, and it's designed to cover the loss of the single biggest thing connected to the grid at any one time. On this day, that reserve was about 1,000 megawatts. The best way to think about it is like having one spare tire in the boot of your car. You're ready for a puncture. But here's the kicker. This wasn't one puncture. When you add in all the smaller local power sources that also tripped offline at the same time, the total loss of power was over 2,100 megawatts, more than double the backup. All of a sudden, the grid had 2 flat tires at once, but only one spare in the boot. The system was instantly and completely overwhelmed. And this graph? Wow. This is basically the electrocardiogram of the crisis. So let's walk through it. Right here at 16:52:33, that's the lightning strike. It causes a fault, but it's cleared in milliseconds. The damage, however, is done. You can see the frequency, the heartbeat, immediately starts to drop as that first power station trips. Then, a second later, Hornsey Wind Farm goes offline and the fall gets much, much steeper. The grid's automatic defenses try to fight back, but it's just not enough. And then, this is the critical moment. The frequency drops so low it breaches a safety threshold. That sharp V-shape you see? That's the exact moment the system decided to cause a partial blackout to stop itself from dying completely. With that heartbeat plummeting, the system was literally seconds away from a total nationwide blackout, a catastrophic collapse. To stop that from happening, an automated, last-ditch defense system had to make a really brutal but absolutely necessary choice. And that system is called low-frequency demand disconnection, or LFDD for short. And the analogy on the slide is just perfect. It's like the captain of a sinking ship ordering the crew to throw cargo overboard. The system has to get rid of some weight, or in this case demand, to save the entire ship. It deliberately cuts power to some of us to save the network for all of us. And here's the trigger point. As the frequency collapsed past 49 hertz and hit that critical line in the sand, 48.8 hertz, the LFD system kicked in automatically. All across the country, virtual switches were flicked, and for a lot of people, the lights went out. And this is who felt it, over 1.1 million customers in total. You can see it wasn't just one place. From London to the Northeast, the system shed its load exactly as it was programmed to do. And it worked. It stopped the frequency from falling any further and stabilized the grid. And incredibly, the grid recovered. The frequency was back to normal within about 5 minutes, and every single one of those 1.1 million customers had their power back on within 45 minutes. So, from a purely engineering point of view, that's a success. But, and this is a huge but, for thousands of people trying to get home on a Friday night, the real chaos was only just getting started. Which brings us to the second, and honestly more baffling part of this story, the absolute chaos on the railways. The big question is, why on earth did a 45-minute power cut lead to more than 24 hours of travel misery? This just lays the whole paradox bare, doesn't it? The grid is back up and running in 45 minutes flat, but the rail network? It sees disruption that rolls right into the next day. We're talking nearly 400 trains canceled, almost 900 delayed. The knock-on effect was just wildly out of proportion. So we have to figure out why. So, the investigation quickly found that the problem wasn't a lack of power going to the train tracks themselves. In fact, most trains on the network just carried on as normal. The problem was isolated to two of the newest, most modern trains out there, the Class 700 and the Class 717. And the reason these brand new trains failed wasn't because of a mechanical fault or an electrical one. Nope, it was a bug, a hidden, unintended consequence that was buried deep, deep down in their control software. And here it is. This quote from the official report is the smoking gun. The train's own software interpreted that brief dip in the grid's frequency not as a temporary flicker, but as a massive safety risk that needed what's called a permanent lockout. Basically, for a minor problem, the software chose the nuclear option. Okay, so what's the difference? This is the absolute key to the whole mess. A temporary lockout is like when your computer freezes. The driver can basically just do a quick reset and get going again. But a permanent lockout? That's designed for something catastrophic, like a fire. The driver cannot reset it. It requires a specialist technician with a laptop to physically go to the stranded train and reboot it. So you can see how this one little software setting just caused utter chaos. Step 1, the grid frequency dips. Step 2, the software on 22 of these brand new trains all at the same time triggers this permanent lockout. Step 3, they all just die, completely disabled, blocking major train lines into London right at the start of the Friday evening rush hour. And step 4, now a handful of technicians have to race around the country from train to train to reset each one with a laptop. It was a complete logistical nightmare. So what did we learn from all this? Well, the event exposed these hidden weaknesses not just in our power grid, but in all the complex systems that rely on it. The final reports laid out a really clear path for building a much more resilient system for the future. Yeah, the lessons were crystal clear. The grid had to rethink its one spare tire policy for an age where you can get 2 punctures at once. It needed to adapt to a future with more renewables that have less of that natural physical inertia we talked about. And crucially, the software on critical things like trains needed to be properly tested for these exact kinds of weird, unintended side effects. Basically, we need to make sure our essential services are actually resilient. And that leaves us with one last big thought. The 2019 blackout wasn't just a failure of power stations and pylons, it was a failure of hidden complexity. So as our entire world gets smarter, more connected, and more automated, it just makes you wonder, doesn't it? Are we really prepared for all the new, smarter ways it can fail?